Hello, my name is Shada Nashat Salim. I'm 17, I'm in grade 12, and I'm from Dubai National School, Al Tuwar. Today I will teach you a lesson in AP Chemistry, which is about standard enthalpy of formation and reaction. To start with, what is enthalpy of formation? Enthalpy of formation is defined as the change in enthalpy when 1 mole of a substance under the conditions of 1 atm of pressure and 25 degrees Celsius is formed from its pure elements under the same conditions. Enthalpy of formation can be seen like this. Delta H is a change in enthalpy. The degrees means that it is a standard enthalpy change, and F means that the substance is formed from its elements. Also, the unit is kilojoules. Before I start explaining this slide, I can tell that you're afraid because of this large table that includes things that you don't understand, but I promise you that it is really easy to grasp the information. The standard enthalpy of an element in its most stable form is 0. Means that if the elements are in the form that they exist in normally in nature, then they have a standard enthalpy of 0. To further elaborate, let's take carbon as an example. Carbon, as in graphite, and carbon, as in diamond. Carbon exists as graphite in nature, so its standard enthalpy of formation is 0 kilojoules. But we rarely find diamond in nature. People take graphite and put it under high pressure and temperature to make diamond, so its standard enthalpy of formation is a number that is not 0, which is 1.9 kilojoules. Now let me erase. You might ask, why does liquid water, which is right here, have a standard enthalpy of formation of a negative 285.83 kilojoules? Doesn't it exist in nature as liquid? We're talking about elements here, and H2O is a compound. Only elements in their standard state have a standard enthalpy of formation of 0, such as hydrogen gas and nitrogen gas and solid zinc. To calculate the standard enthalpy of reactions, we have two ways: the direct method and the indirect method. We will start with the direct method. The standard enthalpy of reactions means the enthalpy of a reaction carried out at 1 atm. Here is the equation, and it is translated to the standard enthalpy change of reactions is equal to the sum of the standard enthalpies of formation of the products minus the sum of the standard enthalpies of formation of the reactants, and it looks like this. Here is the table again. We have to depend on it. We have to use it to be able to solve the question below. Let's see if you can solve this question. Pause this video and give it a try. The question wants us to use the standard enthalpies of the formation table above to determine the change in the enthalpy for this reaction. So we have 2CO gas plus O2 gas, and they will give us 2 carbon dioxide gas. Wait. gas, it will give us 2 carbon dioxide gas. Okay, the equation is delta H Rxn equals this delta H for the product minus the sum of delta H of the reactants. Let's write the standard enthalpy of formation for all of the reactants and products. For CO gas and O2 gas and CO2 gas. Okay, for CO gas, it is negative 110.525 kilojoules. For oxygen, we don't have to check the table because oxygen in nature is gas, so it is 0 kilojoules. Carbon dioxide is not an element, so we have to check the table. It is, carbon dioxide is right here, negative 393, negative 393.5 kilojoules. Okay, this is the product, and these are the reactants. Wait, the reactants. Okay, so delta H Rxn equals the total delta H of the product is 2 times negative 393.5, and we multiplied it by 2 because we have 2 moles of carbon dioxide, as you can see here. Then we have to subtract it with 2 times negative 110.5, because again, as you can see here, we have 2 moles of CO, and if you do the math, it will be negative 566 kilojoules. Okay, we're done with this. Now moving on to the indirect method. For this method, we have to use something called Hess's law, which states that if you add 2 or more thermochemical equations to produce a final equation for a reaction, then the sum of the enthalpy changes for the individual reactions is the enthalpy change for the final reaction. Which means that if we have 2 reactions, 1 and 2, this reaction and this reaction, if we add them together to make a third reaction, which is right here, the third reaction, then the sum of both delta H of the first equation and the second equation will be the delta H of the third equation. So the delta H of the third or the new equation will be the sum of delta H1 plus delta H of the second reaction. Okay. Now, how do we solve questions that need us to use the Hess's law to answer the questions? Okay, so we have to do multiple things. The first one is if you multiply Rxn by a number, multiply delta H by that number, which means that if you multiply the reaction by a certain number, let's say by 3, then you must multiply the delta H of that reaction by 3. The second thing you have to be aware of is that if you reverse or switch products and reactants, then you must switch the signs of delta H, which means that if you want the product to become the reactant and the reactant to become the product, then you must change the sign of delta H and give it a sign that is not how it was previously. So if delta H was a positive value before reversing the equation, then the delta H will be, let's say if it was a negative sign, then it will be a positive sign and vice versa. The third thing is if you add all the numbers, you can cancel elements that appear on both sides. Let's take oxygen as an example. If in a reaction oxygen was a reactant and in another reaction oxygen was a product, then you can simply cancel both of them if they have the same amount of mole. For example, if we have 1 mole and 1 mole of oxygen in both reactants and products, then you can basically cancel them and nothing will be left. But let's say if instead of 1 mole we have 2 moles here, then 1 mole of oxygen will cancel only 1 mole of oxygen in the product, so we will have 1 oxygen in the product. Okay, now let's solve this question. Again, you can pause this video and try to solve this by yourself. Okay, so the question wants us to calculate the enthalpy change in kilojoules for the following reactions, and they gave us 2 reactions. Let's say this is reaction 1 and this is 2. So they want us in this question to add these 2 equations such that we get the third equation. So let's focus here first. We have 3 moles of C, and if we search in these 2 equations for C, you'll find that we only have this C, but we have only 1 mole of C here, but they want us to have 3 moles. So what are we supposed to do? We must multiply this equation by 3, and don't forget to multiply the delta H of that equation by 3 too. So the delta H would be negative 330 kilojoules. So let's rewrite the second equation. It will be 3C plus 3 over 2 oxygen will give us 3CO. Okay, now we have 3 moles of C here, so we're done with this. Now moving on to this, we need Cr2O3 to be a reactant, but as you can see here, we have only Cr2O3 as a product. So we should reverse the first equation, and by reversing the first equation, this will become the reactant and this will become the product. And the delta H, its sign will change. So it was a negative value, it will become a positive after reversing. So if we rewrite it, it will be Cr2O3 will give us 2Cr plus 3 over 2O2. And as you can see here that here we need only 1 mole of it, and we have 1 mole of it right here, so we don't have to multiply the first equation by anything. So now we are on the last step, which is adding the 2 equations. We can cancel certain things such as 3 over 2 oxygen and 3 over 2 oxygen because both of them have the same element, which is oxygen, and both of them have the same value, which is 3 over 2, so nothing is left. And we can't cancel anything, so let's write the final equation. It will be 3C plus Cr2O3, and they will give us 2Cr plus 3CO. Now let's check if what we did was correct. We have 3C right here. It is here. Cr2O3 is here. So we're good. 2Cr right here and 3CO here. So we finished, but we have one thing left, which is calculating the enthalpy change in kilojoules. How do we do that? We basically add these two together, which are the values of delta H after fixing them. So the delta H of the final equation would be 1130 plus negative 330, which will give us 800 kilojoules. So the delta H of this equation is 800 kilojoules. Now we're finally done with this lesson. I hope that you understood everything, and thank you so much for listening.